We are Team 1009 from Texas A&M University, and we chose Prompt B, an AI Ouroboros. My name is Daniel Bruni.
My name is Justin Chen, and we have a third team member, Taro Omori.
As an overview, for our model for Prompt B, we wanted to address the degradation in quality of outputs by generative AI when it's used recursively to train new models by using an SIR simulation. In our SIR model, we treat polluted data or data that's come out degraded from AI models as an infection that spreads to the rest of the data population. We chose to use an SIR model mainly due to parallels that we noticed between the recursive spread of degrading quality in our data with infectious disease spreading that we see modeled in real life today. To define our terms S, I, and R, S is the proportion of the data that is human-generated content that is clean and still susceptible to infection. I is the proportion of AI-polluted content, so this is content that's been run through a model and infected. And R is the proportion of recovered content that has been flagged by human intervention but not yet added back to SFT. SFT is the proportion that is clean data. The speed at which clean data is contaminated is dependent on the volume of existing AI content, how much clean data is left to pollute, as well as the rate at which AI interacts with and corrupts data, which is represented by beta. The term is subtracted as it is an outflow. The speed at which data is added back into SFT depends on R, how much data is in recovery, multiplied by alpha, which is the rate at which humans clean data and restore it back to S. This term is positive as it's an inflow. An observation is that clean data decreases when AI dominates, a large beta value, and increases when humans restore information quickly, a large alpha value. I of t is the proportion of data that's been polluted by AI models. This is given by clean content being infected at a rate beta multiplied by S and I for the influx of data into I of t. We also have the rate gamma at which humans identify and flag data multiplied by I as data leaves the I of t category, which is why it's subtracted. As we can see, the rate at which polluted content grows depends on how much clean data remains, as well as how fast humans can flag corrupt content. Mathematically speaking, if beta S is greater than gamma, then the pollution will spread. If beta S is less than gamma, then human intervention wins, and we tend towards clean data. Lastly, we have R of t, which is the proportion of recovering data that has been flagged by human intervention, but not yet added back to the clean S of t data pool. This is important because in a practical scenario, there'd be a time delay between how fast humans can identify the data and when they restore the polluted data back to its clean state. And since we're modeling with respect to t, this adds more realistic oscillations into our model. The rate at which R of t changes can be defined as the influx of data to the recovering status, which is gamma, the rate of identification, multiplied by the infected population. We also have alpha, the rate at which flag data is cleaned and returned to S, multiplied by the R population, which is subtracted as it's an outflow of data. As a final representation, our model can be visualized as a circular pattern moving from S of t to I of t to R of t at rates beta Si moving from S to I, gamma I moving from I to R, and alpha R from R of t back to S of t. A useful tool for us is a threshold based on what we defined earlier with beta S being greater than or less than gamma. If we divide both sides of the inequality by gamma, we can define this threshold as beta S divided by gamma. We say if t is greater than 1, then beta S is greater than gamma, and AI-generated content spreads faster than humans can intervene, thus leading to collapse. If the threshold is equal to 1, then beta S is equal to gamma, and thus the model is in an unstable equilibrium where any small imbalance would cause a large effect in the corresponding direction. If t is less than 1, then beta S is less than gamma, and AI-generated content is cleaned by humans faster than it can spread, thus the model tends towards clean data. An important note is that we define collapse not necessarily as a 100% infection rate, but rather an equilibrium point where a finite polluted fraction of the population is infected. This is because we're asked to explore how this system interacts with human-generated content and human intervention. We want to model a more realistic situation where humans can certainly intervene with the data pool and training process such that gamma is a non-zero value. This is because if AI models were allowed to go to perpetuity, it would be relatively certain that it would lead to a 100% infection rate with no human intervention. Here are our main assumptions for our models to work. Some of the three that I'll highlight is that this is a closed system of data, which means no external flow. We assumed constant rates that ignore feedback loops in alpha, gamma, and beta. And we also assume that humans can accurately identify AI-generated content, meaning we don't need a stochastic process to model gamma.
We implement this SIR model in Python using the fourth order SCUDEM method to plot various situations by varying the rates beta, gamma, and alpha. On the left, we see a situation of collapse, and on the right, we see no collapse, where human intervention cleans the data faster than AI can pollute. It's important to note that we use different initial conditions for both of these. In the first one, we set the initial proportion of AI polluted data to 0.01, and in the second one, we are setting it to 0.5. We do this purely to emphasize the effects of these constants and to see some drastic change in the model due to human intervention. Since our constants are unknown in the real world, we want to be able to explore the behavior of our model as the constants change. To do this, let's first plot a graph of I star versus a function of beta. I star is the long-term polluted equilibrium, and we want to see how that changes with respect to beta. I'm not going to get into the derivation for this for time purposes, but in the end, we get the expression that I star equals this fraction, and we can plot this using Python. We see clearly that as beta increases, the long-term equilibrium of polluted data becomes non-zero when beta equals gamma. That is exactly this orange dotted line, which is the threshold. Past this threshold point, the model collapses with increasing fraction of polluted data as the contamination rate beta increases. The parameter alpha determines how large I star is once the model collapses. So increasing alpha increases the population of polluted data I star because it increases the amount of data in circulation that is susceptible to pollution. We can see this with a bifurcation surface where we plot I star versus beta and alpha, and we get this 3D surface showing that I star is maximized when we increase alpha and beta. And then we can perform a Monte Carlo simulation illustrating the different possible parameters and their resulting proportion of infected data. To do this, we graph the scatter plot of I star versus the threshold, which we defined earlier as beta s divided by gamma, and we do 300 Monte Carlo draws for the parameters beta and gamma. In the prompt, we are asked to examine what happens when multiple AI models interact. To explore this, we are going to introduce additional infected compartments that represent AI models trained on previously generated data. So now we have I1, I2 through IN. We are also going to introduce this new constant, mu, which is the interaction rate, how much each model reuses each other's output. On the right here, we have the differential equation form. This is a general form, so that we have n plus 2 number of equations. However, for simplicity purposes, we will only consider 2 AI models. Here we have that model exactly, which is a system of 4 differential equations. It is important to note that our initial conditions here are going to be I of 1 naught is going to be 0.02, beta 1 is 1, I of 2 naught is 0, beta 2 is 0. What this means is that the first AI model has just a little bit contamination to start with, while the second one has no contamination and does not spread anything. It is important to note that in these graphs we ignore human intervention rates, so we set gamma equal to 0 in order to fully capture the interaction effects on total collapse. In figure 7, notice how model 2 starts with 0 polluted data and is dragged upwards by model 1. In figure 8 on the right, we see that higher interaction rate mu causes more aggressive collapse as they quickly approach the same equilibrium. Lower interaction rate takes longer before they converge to equal proportions of polluted data. Now we do want to see the effects of human intervention on 2 interacting models. So we set gamma 1, gamma 2 to non-zero values, and we see that with lower mu, which is lower interaction rates, the model equilibriums are much further apart. One of them is much cleaner than the other one. When you increase the interaction rate, the equilibriums become closer and closer, more aggressive, converging towards the same equilibrium. So it makes sense that as mu increases, the difference between proportions of polluted data between 2 interacting models tends to 0. To illustrate this further, we perform another Monte Carlo simulation of the difference between 2 equilibriums I1 star minus I2 star against the interaction rate mu. Clearly, we see that more interaction, or higher mu, leads to more similar long-term behavior. Thus, in this way, we can finally define what total collapse means mathematically, and that is when I1 star minus I2 star is 0. Here are some limitations to our model, some of which we already mentioned in our assumptions earlier. Finally, in conclusion, If we want AI to stay creative and reliable, humans must intervene with data produced by these AI models. Otherwise, the system will slowly reinforce its own mistakes over and over again and tends towards total collapse.